Okay. So, yesterday was all about the periodic law and the periodic table, how they found patterns of behavior. And then once they found a group of things that had similar properties, they gave them a name. Was that a pretty good summary of what we did yesterday? How they know, what they found the properties, how they organized them, and then they gave them names. Okay. So today we're going to start talking about why. Okay. Why do the properties repeat? Okay. And to do a why question, you always have to look at what the little tiny pieces are doing. Right? Well, in your head, because you're never going to see them. So draw little tiny pieces in your head. So, when two atoms interact, what parts are going to run into each other? So, what's going to run into each other is the electron cloud. So the nuclei are never going to touch each other. The thing that identify what you are, the nuclei, they don't touch each other, but the electron clouds do. So I'm not going to change the identity of the atom when they run into each other, because the protons are going to stay the same, but the electrons can move around. And actually, it's not all the electrons. Because electrons have this charge, right? So if you try to bring electrons next to electrons, they're going to repel. So it's not, the two electron clouds are not going to be able to completely overlap each other. They're going to push each other apart. So the only part that's actually going to touch is the outside. Only the outside orbitals are going to touch. Did you know the orbitals fill up in a regular pattern? You may have heard it. It sounds something like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. I think that's the pattern, with a few exceptions. So that means if the orbitals fill up in a regular pattern, then the outside is going to fill up in a regular pattern. So we can put those statements together to talk about properties. Since the ones that are important on the outside and what they look like on the outside repeats, that means the properties are going to repeat. Right? If the things responsible for it repeat, then you're going to get a repetition of what happens. So if we want to predict behavior for elements and atoms, we need to look and see what their outside electrons look like. Right? So the outside electrons, the ones in the outer energy level, the ones with the highest number in front of them, it's always going to be S's and P's. Because S's and P's always have the highest number. Because D's are always 1 behind and F's are always 2 behind. So S's and P's are going to be the highest ones. Okay? And those highest ones, as we talked quickly last chapter, gave that word out that you'd heard someplace before, your 8th grade or 9th grade, those are called valence electrons. It's the electrons in the outer energy level, and it has to be S's and P's, because the biggest number is always going to go in front of an S or a P. So, like I say, the only place I've ever seen valence used outside of class, they usually pronounce the difference as valence. And if you've got curtains, and they put that second frilly little curtain on the outside of it, that's just for show, it's called a valence. So, interior decorators use it. Okay. And the electrons that aren't valence electrons, are called core electrons because they're in the core, deep in the center. And this was the whole basis for our shorthand, right? The inside looks like this noble gas. The outside looks like this, this, and this. So the core electrons are going to be the noble gas ones. The valence electrons are going to be the ones after the noble gas in the noble gas configuration. So if I were to look at, say, the alkali metals and their electron configuration, hydrogen would be 1s1, lithium would be 1s2, 2s1, sodium would be 1s2, 2s2, 2p6, 3s1, potassium would be 1s2, 2s2, 2p6, 3s6, 3s2, 3p6, 4s1, and we can guess that rubidium is going to end at 5s1, cesium at 6s1, and francium at 7s1. Okay? Okay? So all of these react explosively when you put them in water. Why? Because they have one electron in their outer energy level. And something has to happen with that. Right? We got to see what one electron in the outer energy level means, right? So because if it's responsible for the outside ones, we got to see what it means. Yeah. Actually, it's going to be 8s. Rubidium is the 5s1.
Oh.
1, 2, 3, 4, 5, 6, 7. Yeah, I did all 7 of them. Oh. Okay. So that S1, that single electron in the outside energy level has to be responsible for why alkali metals behave the way they do. Okay. So that when we write the shorthand, we just say, oops, sorry, let's go back up. We just say argon 4s1. Okay? Because the core is argon. The outside is 4s1. The core is not going to do anything. The S1 is. Okay? So that's where we got to get to. What does S1 tell me is happening? Okay? At the other end, if I do the noble gases, helium's 1s2, neon's 1s2, 2s2, 2p6. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. I group them by energy level because you can see that they're all going to be end in S2p6. Oh, except for the first one. Why does the first one not end in S2p6? Okay. So, what can we say is true about all the noble gases? Okay. Think about the next electron. Where's the next electron going for each one of those? Going into the next s orbital, right? So their outside energy levels are full. And that's why noble gases don't react. Is because they have full outer electron configurations. And what do we say about full? Full was stable and low energy. So the reason why noble gases don't react is their outside is full. And they don't want to change it because that's low energy. Okay? So that's where we're getting to, those types of things. So we can do this one. We know enough to do this one. We just got to figure out what's going on with the alkali metals. Okay? So let's just make sure we're all on the same page because I'll see how much of the 5.2 stuff you read about that I have to review because it was all about the D, the F blocks. Now I want to tie those together. So if the electron configuration was radon 5f7, 7s2, how would you classify that atom? Okay, so what orbital is filling? F7, right? So which one is where F7 is filling? That's that stuff down at the bottom, right? So that's an inner transition metal, right? Because the bottoms are Fs. I have to figure out which element it is. The bottoms are F's. Okay? Which is the electron configuration of a halogen? Okay, the hard part, you have to remember which ones are the halogens. I only mentioned it quickly yesterday once, but we're going to talk about them all the time. It's an important name. Halogens are group 7A or 17, whichever way you want. So it's this column. And this column, we know everything has to end in P5. Okay, so and N is the energy level, right? So they're all going to, so chlorine would end in 3s2, 3p5. Right? Bromine would be 4s2, 4p5. What is this little N minus 1 D7? Because D is always one behind. Okay? So if I had this, by the way, this is not going to happen because you can't fill up P6 before you fill up D. Well, you can. It's called an excited state, and it's going to fall back down to a ground state and give you little pieces of light when it does that.
So we put in the N for the fact that it's representing the family, and because those are variables and they could be different.
No, okay. The N is the energy level. Energy level. And yeah, so yeah, because here this is 4, that's 3. So that'd be 4s2, 3d7, 4p6. So they're saying that N just means the energy level. Okay, that's what the N minus 1 works. And for F's, it's going to be N minus 2 because they're 2 behind. Okay. Okay, manganese. Okay, I'll give you a hint. It's not D, because that's magnesium. Oh, I'd put that on the test too, because somebody's going to make that mistake. Okay. Okay. Okay, so we know the noble gas before it's argon. Okay, we know that this is 1, 2, 3, 4 rows down. So it's going to be 4s. But we just did N minus 1 for Ds, right? Ds are always 1 behind. So it's got to be C. Okay, it's always got, so B is wrong because it doesn't go 4s 4D, it goes 4s 3D. Okay, so which of those two would have the same chemical property? How the heck am I supposed to know that? Because what's responsible for everything? The outer stuff, right? So, the outer one, that's a P5, that's a P6, that's a P4, that's a P5. It's got to be the 5s. So 1 and 4, which is a B. They're all halogens. We just said that P5 is the halogens just a second ago, right? So, it's actually it's part of the naming, so it gives them a hint when they're doing stuff. Hey.
So, like, how did they name them before they knew they were halogens?
Oh no, they knew they were halogens. Halogen means salt former. So they're always parts of salts. You never find them by themselves. So you find chlorine hooked to sodium. You never find chlorine by itself. The only place you find chlorine by itself is when you're bubbling it into water to purify the water. And you do not want to be around the chlorine because they used it. That was the first gas they used in World War I for gas attacks. So it just, eats your lungs away. Breathing's overrated. Okay. So now we're going to talk about some properties, how things behave, and patterns in those properties. Okay. And we're going to you're going to have to know the patterns and be able to explain why they are what they are. Okay. So patterns that we're going to look at. One of the patterns is in atomic radius, atomic size. There's a pattern to atomic radius or atomic size. What do you think atomic radius or atomic size is? Yeah, how big an atom is? Okay. It's not a surprise definition. Bigger radius gets you a bigger atom. By size, we mean volume, not mass. Okay. The second trend we're going to look at is called ionization energy. Okay, and ionization energy is a lot like the photoelectric effect. Okay? Ionization energy is the energy to remove an electron. The reason why it's not the photoelectric effect is because it's from a gas. You turn it into a gas first, and then you try to take the electron off of it. So the more attracted the electron is, the bigger the ionization energy would be. You'd have to put in more energy to tear it apart. The less attracted it is, the lower the ionization energy is. So ionization energy is a measure of how hard that electron is being pulled on. Okay. Electronegativity is still another attraction, but it's an attraction for the electron in a compound. It's not the attraction it has for its own electron, it's the attraction it has for its neighbor's electron. How hard does it pull on the neighbor's electron? And then ionic size. By ionic size, we mean how big they are after they've lost that electron. They change. Some things change sizes dramatically when you move the electrons around. Sometimes it's a minor effect. Sometimes it can be really major. Okay. So those are the 4 trends we're going to investigate over the next couple of days. And we're going to look for periodic trends. So if I ask you what is the periodic trend, I'm asking how do those vary as you go across a period? How does the size change as you go across the period? How does the ionization energy change as you go across the period? How does electronegativity change as you go from left to right across the period? Yes, we read English, not Arabic or Hebrew, so we go from left to right. We say across. Don't read Japanese, so we don't go up and down. We don't read Hebrew or Arabic, so we don't read right to left. We're talking left to right. We say across.
So the table will be backwards?
Yeah, in Hebrew it'd be backwards. And it worked just fine. Okay. Group trends. Well, if a periodic trend is what happens as you go across a period, what do you think a group trend is? How those 4 things vary as you go down a group. What happens to the electronegativity as you go down a group? Okay. So as you go across, as you go down, what happens to size? What happens to ionization energy? What happens? So that is what happens to how hard it is to pull off an electron. Okay. And then why those trends are there. I need to be able to explain why in terms of little tiny pieces we can't see. Why is this atom bigger than that atom? Now, we don't know any of the patterns yet. You're going to discover those through your reading and the activity over the next couple of days. Okay? But I want to start off with the why. I want to start off with the theory behind all this. Before you see the pattern, I think it's a good idea to have an underlying reason. Okay? And here's the why. For all of them, the positive nucleus pulls on the electrons. And all of those things, the size, the electronegativity, the ionization energy, is all just a measure of how hard those electrons are being pulled. The harder they're being pulled, the higher the ionization energy. The harder they're being pulled, the closer in they'll get. Right? So all of those are about the attraction between the nucleus and the electrons on the outside. So to explain the periodic trend, so as you go across a period, the charge on the nucleus gets bigger. If you think about it for a second, yeah, of course it does, because go across, it's the number, right? So lithium has 3 protons, neon has 10 protons. Okay? Neon's got a bigger pull than lithium. Everybody okay with that? It's not a hard one to figure out even, is it? Okay? Where are the electrons? Well, they're all, the ones we're worried about are all in the same energy level. Okay, right? It's S2P6. No matter where you're at, the D's are inside. They're 3, right? So the outside is still 4s, right? So if the outermost electrons are in the same energy level, they're not going to be in the same place. Okay? Because to have the same amount of energy falling off a ladder, if I fall off the ladder here on Earth, on the moon, to get the same damage falling off a ladder, my ladder would have to be 6 times taller. Because gravity is 1/6 as strong. Okay? So to have the same amount of energy, I need to be 6 times higher because I'm not being pulled this hard. Well, the same is going to be true for the atoms. Those 3 protons in lithium are not going to pull in the second energy level as much as the 10 electrons on neon, the 10 protons on neon. Does that make sense? The 10 is going to be able to pull more than 3. Now we do have so the outer electrons are pulled stronger. Now those electrons, we didn't just add protons, we also added electrons. So electrons will repel each other. So you don't feel the full impact of those extra 7 protons. More than tripling your number of protons. You don't feel it all because some of the electrons pushed it away some. So that's going to be our reason for periodic trends. As you go across, you get more nuclear charge, so the electrons are pulled harder. Okay. So positive nucleus pulls on the electrons. What about group trends? Oh, I didn't want to go there. Click on something, it doesn't go there. Okay. So we say which direction we're talking about a group? We're going to go down a group. And what happens to the electrons as you go down a group? Not only do you have more electrons, think about electron configuration. How is sodium different than lithium? Higher energy level. Right? Lithium's outside is 2s1, sodium's is 3s1. So if you add energy levels, the outermost electrons are not as attracted. Now, we do have a little thing though, but what we forgot about the protons, Mr. Green. Not only does sodium have another energy level, it also has 8 more protons. Why don't the 8 more protons win over the extra energy level? Shouldn't 8 more protons pull more? Well, they don't pull more because of something called shielding. And it's actually a pretty simple concept. What is the working theory behind a shield? Okay, so you're protecting yourself by blocking. How does it block it? It just gets in the way. Someone's swinging at your head, the shield just gets in the way. Well, what's going to get in the way is the inside electrons, those core electrons. The electron, the outside energy level, has layers of electrons underneath it. Now, I'm going to draw this as a Bohr atom because it's easier to draw as a Bohr atom. We really know it's Schrodinger's, but Bohr does a decent job of explaining this. Okay. Does that make sense? We picked the easiest model we can get away with. And Bohr explains a lot. If we need to, we can go into the quantum mechanical, what the quantum mechanical part will look like, but we don't need to right now. Okay. So this is a potassium atom. How could you tell that's a potassium atom, Mr. Green? Well, because it's on the first, second, third, fourth energy level with 1 electron. That's potassium. Okay? Right. But, and it says look through, it's really, there's a negative charge between it and the nucleus. So if you got a negative charge between you and the nucleus, that negative charge between you and the nucleus gets in the way. If I go across, but if I'm in the same energy level, if I went to calcium, I'd add another electron, but I wouldn't change the shields. Right? The shield would be the same. The first 3 energy levels were in the way of potassium. The same 3 energy levels are in the way of calcium. So a second electron has the same shielding. So as I go across a row, as I go across a period, the shielding is constant. It doesn't change. And that's why we only had to worry about nuclear charge as we went across the period. We didn't talk about the electrons at all, that we're adding extra electrons. We only talked about nuclear charge going across the period because the energy level stays the same the whole way, so the shielding stays the same way the whole way. And that's part of the thing that caused Bohr some grief, is trying to do the math with those electrons in the way. It's tough. Even if they're in perfectly circular orbits, much more complicated when they're probability waves. Okay. So, in the first energy level, hydrogen. How much shielding for hydrogen? Well, there is none. Okay? But as the energy level changes, the shielding change. So hydrogen had no shielding. Lithium has a shield. So there's 3 times as many protons, but there's electrons blocking those 3 times as many protons, so it ends up that the shield is more effective than the extra charge. Does that make sense? The shielding does such a good job of blocking that 8 times the charge is, that extra 8 charge is not going to come out. Right? Sodium has 3 shields. Or it has 2 shields. Potassium has 3 shields. So the lower down the group, the more energy levels, more shielding, less attracted. Because those inside electrons get in the way. And part of the reason why the shield gets so good is because you've got a lot of positive charge. You're going to pull those electrons in close so they don't have to block as much volume. If you let them go out far, there's lots of holes in between them. You pull them close together, there's fewer gaps between them. Does that make sense? Sort of like tight splits and wide splits at the line. When you're kicking field goals, you don't want wide splits. Okay? Running the veer, you do. Okay. So which one of these is not correct? One of these things is not like the others. Come on now, can you tell me which one? Pick which thing. See, there's 3 of them. Oh no, it's got to be 2 of them wrong. No, only one of them's wrong. It's A. Shielding doesn't change as you go across the period. Shielding increases as you go down. That's true. Nuclear charge increases as you go down, but shielding beats it. The shield wins out over the increased nuclear charge. And actually, the zigzag line is actually there because shielding wins over nuclear charge. That things hold on to their electrons less and less as you go down the table because shielding beats nuclear charge. Nope, because that's because it's 4. And the next thing you're going to do is 4. We're going to do 3D inside, and then 4. No, because the shielding that goes back inside and the shielding's not affected, doesn't change much, doesn't change it. So we're not going to let the D's change our shielding. You'll see minor effects, but not ones we can predict.
So like potassium and krypton have the same amount of shielding?
Potassium krypton has the same amount of shielding, but potassium is holding that shield in with 19, krypton's holding it in with 36. And 36 is going to do a better job than 19. Okay. One last thing we have to define. Atomic size. We said our first trend was going to be atomic size, how big the atom was. Where do you start measuring? Okay, so I start in the nucleus. Okay, where do I stop? The electron cloud doesn't have an edge. Right? There is no, if you want 100% probability, you got to circle the universe. Okay. So, could you, if I asked you to measure the distance from here to the edge of that fog bank, could you do it? Because would you know when you were in the fog and when you weren't, right? So you see the electron cloud is a problem when you talk about how big it is. They solved this problem by measuring 2 atoms. Say, well, why 2 atoms? Well, on 2 atoms, there's a piece I can find in each one. I can find the 2 nuclei. Right? I can find the 2 nuclei, and then I can use some geometry that half the distance between the nuclei would be pretty close to the radius. It's not going to be an exact measure because they overlap a little bit when they bond, but it's going to give us a pretty good measure of how big those atoms are. Bigger atoms would be further apart. Smaller atoms would be closer together. So the atomic radius is half the distance between 2 nuclei because we can measure where the nuclei are. We can't measure where the edge of the electron cloud is. So we say we're measuring atoms, we never measure one at a time. We have to measure them two at a time. So tonight you'll read about these trends. Tomorrow you'll discover those trends. Does that make sense? That's the plan. Because these trends are, well, if I trend in how they behave, it's going to tell us how they react. So, have a good one.